Welcome back to Mechanical Engineering Made Simple.
It's great to be back.
Today we're looking at two concepts that, on the surface, seem like they're from completely different worlds. On one hand, you have the very real, very physical act of twisting a piece of metal until it breaks, torsion.
Right, very hands-on.
And on the other, we've got a way to analyze entire structures using, well, what sounds like pure imagination.
It does have that feel, doesn't it? We're diving into torsion in circular shafts, and then we're making a leap into energy methods, and specifically something called virtual work.
That's the word that got me. Virtual. It
Yes.
sounds more like a video game than a tool for, keeping a bridge from collapsing. So our mission today is to decode these two engineering superpowers, transmitting huge amounts of power through a simple twist and predicting the future using these imaginary scenarios.
That's a perfect way to put it. And they're actually connected by a really core idea, efficiency, or if you want to be a little more direct about it, laziness.
Laziness, I like that. Physics is lazy.
Fundamentally, it always wants to find the path of least resistance, the lowest energy state.
Okay, let's start there with laziness and torsion. Looking at the source material on circular shafts, one thing just jumps out. Drive shafts on trucks, propeller shafts, they're almost always hollow tubes. My first thought is, a solid bar of steel has to be stronger. Why would you take material out?
Yeah, that's the classic intuitive thought, right? More is better. If I'm building a wall, I want it to be thick and solid. But with torsion, that extra material in the middle is, well, it's pretty much useless.
Useless how?
To see why, you have to picture the stress inside the bar as you twist it. The load isn't shared equally, not at all.
So who's doing all the work?
The material on the absolute outer skin, the circumference, the shearing stress, which we call tau, it varies linearly from the center to the outside. That means at the very core, where the radius is 0, the stress is also 0.
So the steel in the middle is literally doing nothing.
Exactly. It's just a passenger. It adds weight, which hurts your fuel economy, but it contributes almost nothing to fighting the twist. It's just going along for the ride.
The text mentions a critical term here, Jay. The polar second moment of area. It's a bit of a mouthful. What is that in simple terms?
Think of J as a rating for how resistant a shape is to being twisted. It's like its torsional stiffness score. And the math tells us that this score, this J value, goes up dramatically the farther you move material away from the center.
So by hollowing out the shaft, you're pushing all the working material to the edges, which gives you a much higher J score.
That's it, exactly. You get far more stiffness for every kilogram of steel you use.
There was a really concrete example in the notes that put a hard number on this. It was comparison between a 25-centimeter solid shaft and a hollow one designed to replace it.
Right, a classic problem. The key constraint was that both shafts had to withstand the exact same maximum shear stress. For the hollow one, the outside diameter was twice the inside diameter.
So you swap this heavy solid bar for a tube. What's the payoff?
It's not just a little lighter. You get a mass saving of around 21%.
21%.
But
That's not trivial. In automotive or aerospace, that's a massive gain.
it's the difference between a competitive design and one that's obsolete. A 21% weight saving on a major component like that. It means less fuel, less wear, better performance, and you haven't sacrificed any of its torque carrying ability.
Okay, so we hollow things out because the center is lazy. That makes perfect sense. But what happens when we twist them too far? The source material gets pretty graphic about how things fail. It seems steel and cast iron go about it very differently.
Oh, completely differently.
Yeah.
And it all comes down to whether a material is ductile, like a mild steel, or brittle, like cast iron. You can even see it if you twist a piece of chalk.
Right, the text had this great image of the cast iron shaft breaking in a perfect spiral. It looked like a corkscrew. Yeah. Why that shape? I thought we were just twisting it, not pulling on it.
And that's the beautiful counterintuitive part. When you apply a pure twist, a shear force, you are also creating tension, a pulling force. It just happens at a 45-degree angle to the axis of the shaft.
Wait, so twisting something is also stretching it diagonally?
Precisely. If you draw a little square on the side of a rubber hose and then twist the hose, the square deforms into a diamond. The points of that diamond are being pulled apart.
Okay, I can picture that. The diamond gets longer.
Exactly. Now, a brittle material like cast iron is actually pretty strong in shear. It doesn't mind that sliding force so much. What it absolutely hates is tension. It's very weak when you pull on it. So the moment that diagonal tension reaches its breaking point, pop, the material unzips.
And since that tension is at 45 degrees, the crack follows that 45-degree path and you get a spiral.
You've got it. It's like a signature left at the crime scene.
Yeah.
You see a spiral fracture on a shaft, you know, instantly it was a brittle failure caused by tension.
And what about the steel? Why no spiral?
Because mild steel is ductile. Its weakness is the opposite. It's actually weaker in shear than it is in tension. It gives way to that sliding force much more easily. So when it fails on the plane where that shear stress is at its absolute maximum.
Which would be where?
Straight across,
Ugh.
perpendicular to the length of the shaft. It just shears off. It's a flat, clean break, almost as if it were cut.
That's a fantastic diagnostic tool. A spiral break means brittle tension failure. A flat break means ductile shear failure.
Exactly. And of course, in the real world, it gets even more complex. A propeller shaft is also pushing, so it's under compression. A turbine shaft might be bending under its own weight.
So you have to combine all those different stresses.
You do. You have to calculate what are called the principal stresses to see the full picture and predict when and how it will actually fail.
Speaking of the full picture, let's pivot now. We're leaving the world of twisting metal behind, and we're stepping into, I guess, the matrix. This idea of energy methods and the principle of virtual work.
It's one of the most powerful and, I think, elegant ideas in all of mechanics. But it can be a little strange at first.
I'll admit, the definition in the source material felt like a bit of a riddle. If a system in equilibrium is given a virtual displacement, the net work done is zero. My brain just hears imaginary movement and gets skeptical. How can that solve a real problem?
It sounds like cheating, doesn't it? But think of it less as imaginary and more as a what-if test. You have a structure, it's sitting perfectly still in equilibrium. We then say, okay, what if this one point moved an infinitesimally small amount? Let's call that amount delta.
But it doesn't actually move that amount.
No, it doesn't. But by pretending it does in the math, we can create an equation. We can calculate the work that would be done by the external forces like gravity during that tiny imaginary movement, and we compare that to the internal strain energy that would be stored in the bent beams. Since nothing is actually moving, the two have to perfectly balance out. The total work has to be zero.
So it's a balancing act. You nudge it in your mind, and the math tells you exactly how much the structure is internally pushing back.
That's a great way to think about it. It lets us find things like deflection without having to solve incredibly complex force equations. The classic example is a cantilever beam, like a diving board. You want to know how much it sags when you stand on the end.
And instead of just measuring it, we use this virtual work method.
We do. We integrate the bending moment multiplied by the virtual curvature along the beam, and the math gives us a very famous result. The deflection is WL cubed divided by 3EI.
I want to stop on that formula. L cubed, length to the power of 3.
That's the killer. It's the most important variable in the equation by far. If you double the length of your diving board, you don't just get double the sag.
2 cubed is 8. You get 8 times the sag.
8 times. That's why engineers are so obsessed with span lengths. Even a small increase in length makes a beam dramatically weaker, or, well, floppier. The effect is exponential.
Wow. Okay, that explains a lot.
Yeah.
Now, this all gets really critical when we move from things just bending elastically, bouncing back to talking about plastic design. This is about total collapse.
Right. Now, the stakes are much higher. We're not asking, will it sag an inch? We're asking, will the whole building fall down?
And this section was kind of terrifying. We're actually designing for the point of failure.
We are designing to predict the point of failure with absolute certainty. When a steel beam reaches its limit, it doesn't just snap. It forms something we call a plastic hinge.
The text described it almost like a door hinge. The beam just folds at that point.
It does. It can still resist a certain amount of force. We call that the plastic moment, or M sub P. But it can rotate freely. And if you get enough of these hinges forming in the right places, your stable structure suddenly becomes an unstable mechanism. And down it comes.
The sources show it's not just one way for it to fail either. There are different failure modes.
Yes. Take a simple rectangular frame, like a goalpost. If you push on it from the side, the top beam could buckle downwards in the middle. We call that the beam mechanism.
Yeah. The entire frame could just lean over sideways,
Yeah.
right? Like it's being pushed over. That's the sway mechanism.
Exactly. Or, and this is where it gets dangerous, it could do a bit of both at the same time.
The combined mechanism. And here's the rule that ties back to our theme of laziness. The structure will always fail by whichever mechanism requires the least amount of force.
It will always find the easiest way down. Nature wants to use the minimum possible energy to collapse it.
So as an engineer, you have to be a detective. You use virtual work to check every possibility. You calculate the load needed to cause the beam failure, then the load for the sway failure.
And this is so critical. There's an example in the material that shows exactly why. They calculated the required beam strength, that M sub P value, to prevent each type of failure.
Right, let's walk through that. For the beam mechanism to happen, what did the beam need?
It needed a strength of 3.3 kilonewton-meters.
Okay. And for the sway mechanism?
It needed to be a bit stronger, 3.75. So if you only check those two, you'd say, okay, I need to design for 3.75.
But then you check the combined mechanism.
And that one required a strength of 4.375.
So that's the real weak point. The combined mechanism is the one that will actually happen. If you'd only designed for the sway at 3.75, your building would have failed.
It would have collapsed because the structure found a cleverer, easier way to fall down that you hadn't accounted for. Gravity wins.
It's like a strategy game. You have to anticipate all of the steel's possible moves to checkmate it.
That's a perfect analogy. You have to find the failure before nature does.
Before we wrap, there were two other big ideas in this section. Complementary energy and the Rayleigh-Ritz method. They felt a bit more abstract.
They're definitely higher-level tools. We normally talk about strain energy, which is the area under the load deflection curve. It's the energy you store in a spring when you stretch it. Complementary energy is just the area above the curve.
For a simple linear material, aren't those two areas identical? It's just a triangle.
For linear elastic materials, yes, they are numerically the same, but the concept of complementary energy gives us a different mathematical tool. It lets us solve problems by working with the loads instead of the displacements, which can be a huge shortcut for certain tricky problems.
So another tool in the toolbox. And Rayleigh-Ritz.
That's really the precursor to modern computer simulation. If you've ever seen a finite element analysis model, those colorful stress maps of car crashes or buildings, they are built on the foundation of methods like Rayleigh-Ritz.
Which is called the method of minimum potential. We're back to laziness again.
We are. The whole principle is that a structure will always deform into the shape that represents the absolute minimum total potential energy. Rayleigh-Ritz gives us a mathematical way to approximate that shape, even for incredibly complex structures where an exact answer is impossible.
So we basically assume the structure is lazy and then use the math to find its laziest possible shape.
That's a fantastic summary of a very complex idea, yes.
So tying it all together, the hollow drive shaft is an efficient, lazy design. A brittle shaft breaks in a spiral because that's the path of least resistance for tensile failure. And a whole building will collapse via the mechanism that requires the absolute least amount of work.
The thread runs through everything. Physics is efficient.
It's kind of humbling. You think of these giant, powerful structures, but they're all governed by this simple, almost primal drive to find the lowest energy state.
We're basically using geometry and material science to build things that temporarily defy that drive.
Which brings me to a final thought for everyone listening. We think of failure as a mistake, something going wrong. But after this conversation, it feels more like failure is the natural state. The structure wants to collapse. It wants to find that plastic hinge.
That's a deep insight, but it's true. Stability is the state we impose on it. The structure is always looking for an exit, for a mechanism to release its stored energy.
So our job as engineers isn't just to build things. It's to constantly outsmart the universe's tendency to want to flatten everything. We're playing this game of virtual work in our heads to stay one step ahead of physics itself.
It's a very dramatic way to put it, but yeah. That's a pretty accurate description of structural engineering.
I think that's the perfect place to leave it. A fantastic journey from a simple twisting bar to the philosophy of why things fall down.
It's been a real pleasure.
If you haven't already, get over to our YouTube channel, Mechanical Engineering Made Simple, where we post hands-on how-to videos, visual breakdowns, and practical engineering walkthroughs you can actually use. A family that solves together, stays together.